This is video 4 for the light unit. Let's talk about mirrors. A mirror is a surface that is very good at reflecting light. Our eye then sees the light coming into it, so our eye really has no way of knowing if the light is coming directly from an object or if the light has been bounced off of a mirror. Our eye honestly cannot tell the difference. So the spot behind the mirror from where the light appears to be coming is called the image, or also called the image. So even though it's quite different than the pinhole camera image. So the key is to recognize that there's actually no light present at the image's location. So here I have an object. It's an arrow, pretty simple. So light from the arrow is going to leave the arrow, reflect off the mirror, and enter your eye. So if I kind of trace that image back, I can see where the top of this object appears to be. And we can do all different kinds of rays coming off of this thing, reflecting into your eye, tracing it back, so we can get an idea for where that image appears to be. And again, if this mirror is, if you did not know that mirror was there, you would think that the object is at that location, when instead the object is at this location. So that's one diagram. Here's a second diagram showing the same thing, just showing you how we can follow light. What this is it's called a ray tracing diagram. And what we're doing is we're just mapping out where the rays of light go. And it's a very useful tool for helping us study different types of mirrors. So one special type of mirror is something called a corner reflector. So what a corner reflector is it's kind of like a box that has 3 sides to it, and each side is a mirror. So when light bounces into a corner, and then with each wall of the mirror, it then reflects in a path parallel to the path it was projected in. So what's important to understand about corner reflectors is that light always exits parallel to its incoming path. So when light comes in at an angle of, 35 degrees, it exits at an angle of 35 degrees. This will only work if the 2 or 3 mirrors make 90-degree right angles with each other. There are more optical devices other than corners that can do the same thing, reflecting light back in the direction of its source. But the general term for all of these different objects are called retroreflectors. We see these corner or these retroreflectors in materials that are reflective. So think about signs on the highway, how they are kind of shiny. If you were to take a close look at them, you would see that the sign is made up of really tiny corner reflectors. On the highway, those little reflectors along the middle of the highway, it kind of reflects, they look yellow. Those are all made up of tiny little corner reflectors. Safety vests that you may wear if you're working with traffic. The reflective strips on buses. All of those things are corner reflectors. Now, one application for corner reflectors also is for radar. So radar is a form of light. It's just that it's at a frequency that we can't see. But radar behaves a lot like light. So what we do is we put corner reflectors near airport runways to help the pilots locate it. So there's a radar emitter on the plane, and it sends out a radar signal in many directions. So let's say that this is our plane. So it's sending out signals in all directions, even some behind it. And then on the ground, there's going to be a corner reflector. And those special radar signals that happen to hit it are going to come back to the plane. And that helps the plane judge distance from how far it is from that specific corner reflector. We've also placed corner reflectors on the moon. So in the 1970s, when we made some of our last missions to the moon, we placed corner reflectors on the moon. So then what we do is we send powerful laser signals to the moon. So if this is our moon, there's a little tiny corner reflector on it. So we send a laser signal, we train it on that corner reflector. Let me draw that. And then the signal comes back to us. And what we can do is we can use the speed of light and the time it takes to send that signal there and back. So we can say that speed equals distance divided by time. So if we know the speed and if we know the time, we can then calculate the distance. And we can measure accurately how far the moon is away from us. We can also use this in a way to talk about stealth technology. So corner reflectors have to make 90-degree angles with each other. So what we do is we design a spacecraft that avoids 90-degree corners. And since they have no 90-degree corners, any radar that hits the plane will not reflect back to its source, and then the plane kind of becomes invisible to radar. And I'm sure you've seen some pictures of these planes. They look really cool. I think one of our stealth bombers is like that, where there's no 90-degree corners on it, so it looks real boxy, kind of weird looking. Okay, the next thing I want to talk about is how we can slow light down. Light does not always travel at 300 million meters per second. Or another number for this is 182,282 miles per second. Comes down to about 1 foot per nanosecond. When we use the speed of light, these are the numbers we talk about, and usually what we mean is the speed of light in space, where there is nothing for light to interact with. Now, that is a very fast speed. It's fast enough for light to get to the moon in 1.3 seconds, or for the light from the sun to reach us in 8 minutes. So it kind of gives you an idea for how far away the sun actually is. But this is only the speed of light in a vacuum. When light enters material, it slows down. So in air, light travels at about 99.9% of its speed in outer space. In water, light travels at about 75%. In glass, light travels at about 60% or 67%. And there are some exotic materials where physicists have managed to have the speed of light come down close to zero. So what this leads us up to is something called the index of refraction. And this is a comparative technique which compares the speed of light in one material versus the speed of light in a vacuum. So since light slows down in materials like glass, water, we can describe it, or we can compare it to the speed of light in a vacuum. We give this the letter n. And we say n equals the speed of light divided by the speed of light in a material. And this gives us a ratio. So for the value of n, or the index of refraction in air, it's 1.0003. And that is, there's no units because this is a ratio. So there's some more common indexes or indices of refraction. And again, this is a useful tool for helping us make some useful calculations. If I were to take a look at, let's say I have this boundary between some air and water. When I have light that is coming in at an angle, remember that light bends towards the slow. So if I were to kind of measure some angles here, I would have this angle, which I'll call this alpha, and I would have this angle right here, I'd call this beta. And what this does is it gives us something called Snell's law. So if I have the index of refraction from the first medium times sine of the first angle has to equal the index of refraction for the second medium times sine of the second material. So I can then use this to calculate what angle light should be traveling in, or should be bent at, in the second medium. So again, that's Snell's law. A very useful formula. All right, the next thing I want to talk about are mirages. So let's say we have a very hot day. When you look along the road, sometimes you see what appears to be a puddle of water in the road. In the desert, you can see what appears to be a lake close to the horizon. However, in both cases, nothing is actually there. These are examples of optical illusions, which we call a mirage. Remember then how sound was bent by air. When we talked about the ground being warm, sound tends to bend upwards away from the ground because the air is colder above and sound bends towards the slow, so it bends towards cold. When we had an inversion, the ground is cooler, so the sound bends toward it. So exactly the same phenomenon is going to occur with light. So when the air is hot above the ground, then the speed of light is faster than it is in cold air. So even the temperature of air kind of dictates how fast light can travel. So what happens then, it gives us the result that light is trying to bend upwards. Or blue light from the sky can be bent upwards in this way as well, and it gives the illusion that there's some blue light on the ground. So here's what's happening for this mirage. We have really hot air close to the surface of the ground, and above it we have some cooler air. So when we have some light traveling in from the blue sky, when it enters this hot air, it kind of speeds up. So it's kind of bending here, it's kind of bending towards the slow. So it kind of bends back upwards. And when that enters your eye, because your eye cannot tell the difference, you see blue light and you assume that there must be water. When in fact you're not seeing water, you're seeing the blue light from our atmosphere. And, then you get all kinds of tales of people walking for hours and hours trying to get to water in the desert when there's nothing there, it's just a mirage. Okay, that's going to conclude this video. In the next one, we will talk about dispersion.